In 1942, American bombers could find Japanese ships in the Pacific, but hitting them was another matter. High-altitude doctrine collided with haze, evasive maneuvers, and the stubborn resilience of steel hulls. So in the Southwest Pacific, someone proposed an idea that sounded less like aviation and more like artillery. Put a tank gun in the nose of a bomber. It was a solution born not from theory, but from frustration. In 1942, American bombers in the Pacific could find Japanese ships, but they often could not destroy them. Flying from improvised airfields in places such as New Guinea and the Solomon Islands, crews of medium and heavy bombers faced a persistent operational problem. Enemy vessels moved quickly, dispersed widely, and were protected by layered anti-aircraft fire. High-altitude bombing, the doctrine emphasized before the war, proved poorly suited to these conditions. At altitudes above 10,000 feet, bombardiers relied on optical sights and steady flight paths. Over the Pacific, weather, haze, and evasive maneuvers by Japanese ships reduced accuracy. A transport or destroyer could alter course during the long fall time of conventional bombs. Even near misses were often insufficient to disable well-compartmented hulls. Results were inconsistent, and ammunition expenditure was high relative to confirmed sinkings. In response, American units in the Southwest Pacific area began experimenting with low-altitude attack tactics in 1942 and early 1943. Aircraft descended to mast height, approaching at high speed to reduce exposure time. Some crews adopted skip bombing, releasing bombs so they would ricochet across the water and strike a ship's side near the waterline. These methods increased hit probability, but also exposed aircraft to intense small arms and automatic fire. Commanders sought a weapon that could combine the accuracy of direct fire with sufficient destructive power to penetrate hull plating and detonate inside the target. The concept emerged of mounting a large caliber cannon in a medium bomber, allowing repeated aimed shots during a single attack run. The 75mm M4 cannon, originally designed for armored vehicles, offered a possible solution. The M4 cannon weighed approximately 900 pounds, including its breech mechanism. It fired a 75mm projectile at a muzzle velocity of roughly 2,000 feet per second. In tank service, it relied on the mass of the vehicle and recoil mechanisms to absorb firing forces. Adapting it to an aircraft required significant engineering modifications. Recoil had to be controlled to avoid structural damage and to maintain flight stability. Engineers selected the North American B-25 Mitchell as the test platform. The aircraft's twin-engine configuration provided redundancy over water and adequate power margins. Its tricycle landing gear allowed a relatively unobstructed nose section, simplifying installation of a forward-firing weapon. Compared to lighter attack aircraft, the B-25 had sufficient internal volume and structural strength to accommodate the cannon, ammunition, and reinforcement without exceeding safe limits. To install the M4, designers removed the standard bombardier position in the nose. The cannon was mounted along the aircraft's longitudinal axis, slightly offset to accommodate loading and sighting equipment. Structural members in the forward fuselage were reinforced with additional bracing to distribute recoil forces into the airframe. Engineers incorporated a hydraulic recoil mechanism and a reinforced mounting cradle to limit rearward movement of the barrel during firing. Weight distribution posed another challenge. The cannon and its mounting shifted the aircraft's center of gravity forward. To compensate, equipment was relocated aft where possible, and ballast adjustments were calculated to maintain stability within allowable limits. Ammunition storage was restricted. Early B-25G variants carried approximately 21 rounds for the cannon, each round weighing around 15 pounds. Total added weight, including gun, mount, and ammunition, exceeded 1 ton, requiring careful recalculation of performance data. Test firings examined structural stress and handling characteristics. Reports indicated that, when properly installed, the recoil impulse was manageable and did not produce catastrophic airframe distortion. However, firing the cannon created momentary deceleration and required pilot compensation to maintain aim during subsequent shots. The rate of fire was limited by manual loading, typically 3 to 4 rounds per minute. Initial reactions within the Army Air Forces were mixed. Some officers questioned whether a medium bomber should be converted into a specialized attack aircraft with limited ammunition and altered bombing capability. Others doubted the practicality of employing a tank gun in aerial combat conditions. Nonetheless, operational necessity in the Pacific encouraged continued development. The resulting B-25G, followed by the improved B-25H, with weight reductions and additional forward-firing machine guns, represented a deliberate adaptation to regional combat demands. By integrating a 75mm cannon into a proven airframe, American engineers created a platform intended to engage shipping and fortified targets at low altitude with direct, concentrated fire. In the months that followed, these modified Mitchells would be committed to combat in the Southwest Pacific. Their performance under operational conditions would determine whether the engineering calculations translated into practical battlefield results. By early 1943, the United States Army Air Forces had committed to an unconventional experiment, firing a 75mm cannon from a twin-engine medium bomber. The concept appeared straightforward on paper. In practice, it required resolving complex mechanical and aerodynamic problems that had no direct precedent in American aviation. The 75mm M4 cannon selected for installation in the B-25G, Mitchell was originally designed for armored vehicles. It was a semi-automatic, breech-loaded weapon using a vertical sliding block mechanism. After each shot, recoil energy forced the barrel rearward against a hydraulic recoil cylinder and spring recuperator system. As the barrel returned forward, the breech block opened, automatically ejecting the spent casing. The weapon then remained open, ready for manual insertion of the next round. The first live firing test of the installed cannon took place at a controlled range in early 1943. Engineers and flight officers observed from the ground while the modified aircraft approached at medium power. Inside the cockpit, tension was evident, but controlled. One test engineer reportedly told the pilot over intercom, "Hold her steady. We need clean data." The pilot responded simply, "Steady as she goes." When the trigger was pressed, the effect was immediate. The aircraft shuddered, and observers noted a distinct reduction in forward velocity. Instruments later confirmed a measurable drop in airspeed and a brief nose-down pitch. The pilot corrected with elevator input and throttle adjustment. After landing, maintenance crews inspected the nose assembly. Several rivets showed minor loosening, and vibration marks were visible around the mounting brackets. The structure had held, but reinforcement was deemed necessary. Inside the modified bomber, a crew member served as loader. The bombardier position was removed, and the cannon was mounted rigidly along the aircraft's longitudinal axis. Ammunition, stored in racks along the fuselage, consisted primarily of armor-piercing and high-explosive rounds. Each complete cartridge weighed approximately 15 pounds. The loader manually inserted the round into the open breech and secured it before the pilot aligned the aircraft for firing. During testing, loaders reported physical strain when the aircraft maneuvered. "It's manageable in level flight," one noted, "but not if we're banking." Under ideal conditions, the practical rate of fire ranged from 3 to 4 rounds per minute, slower than most field artillery and significantly slower than naval automatic guns. Recoil remained the primary engineering concern. Although the M4 incorporated a recoil mechanism, the impulse transmitted to the airframe was substantial. Each discharge produced a temporary deceleration of several knots. More critically, it introduced a nose-down pitching moment. Engineers recorded control surface deflections immediately following each shot. Pilots required anticipation and rapid correction to maintain alignment for successive rounds. To prevent progressive structural damage, the forward fuselage required additional reinforcement after the first test series. Steel mounting plates were thickened, bulkheads strengthened, and load distribution improved along the fuselage longerons. These modifications increased weight and shifted the center of gravity forward. Ballast adjustments and relocation of onboard equipment were implemented to restore acceptable stability margins. Repeated firing introduced vibration and long-term fatigue concerns. Test crews observed that after multiple rounds in succession, minor deformation appeared in adjacent skin panels. Maintenance officers warned that extended operational use without inspection intervals could accelerate metal fatigue. "We can make it work," one engineer summarized, "but it has to be maintained like artillery, not like a standard bomber." Muzzle blast created further complications. The 75mm discharge generated a pronounced flash and dense smoke cloud. At low altitude, this smoke temporarily obscured forward visibility. In humid conditions, it lingered in front of the cockpit, complicating follow-up shots. The blast also disturbed airflow around the nose, producing brief turbulence. Training exercises revealed additional limitations. Accurate employment required a steady, low-altitude approach. Evasive maneuvers disrupted loading and reduced effective rate of fire. Limited ammunition capacity, typically about 20 rounds, constrained engagement duration. Crews also reported cumulative trim changes after repeated firing. These findings prompted refinement in the subsequent B-25H variant. Weight reduction, improved gun mounting, and supplemental forward-firing machine guns were introduced to balance firepower and handling. By mid-1943, the technical obstacles had been reduced to manageable levels. The structural integrity could be preserved, recoil effects controlled, and crews trained to operate the system. The engineering solution had been established. Its effectiveness would now be determined under combat conditions. Before we begin, take a moment to support the channel. If you value detailed research-based military history told without exaggeration or distortion, consider subscribing. Your support allows us to continue producing in-depth analysis of lesser-known World War II operations. If you find this episode informative, leave a like so others with similar interests can discover it. On June 10, 1943, the first combat sortie by a B-25G armed with a 75mm cannon was launched from an airstrip near Port Moresby, New Guinea. The aircraft belonged to the 5th Air Force, which had been tasked with isolating Japanese garrisons by attacking shipping routes between New Guinea and the Bismarck Archipelago. Intelligence reports indicated a small convoy moving along the northern coast toward WWII. 2 medium transports escorted by a destroyer, the modified Mitchell, its glazed bombardier nose replaced by the solid housing of the M4 cannon, taxied before dawn. Ground crews had loaded 21 rounds, a mix of armor-piercing and high-explosive shells. The pilot reviewed the attack plan, low approach from seaward, coordinated with strafing B-25's Cs and skip-bombing aircraft assigned to suppress anti-aircraft fire. As the formation crossed the coast at approximately 4,000 feet, weather conditions were clear with moderate haze. The convoy was sighted at mid-morning, maintaining a steady coastal track at roughly 12 knots. Japanese ships were arranged in a staggered pattern, the destroyer positioned slightly aft and to port of the transports. The attack began with a descent to low altitude. The cannon-armed B-25 reduced height to approximately 300 feet, accelerating to near 230 miles per hour. Over the intercom, the co-pilot announced, "Range 2,000 yards. Closing." The pilot responded, "Hold steady. We take the lead transport." Strafing aircraft moved first, sweeping the decks with .50 caliber fire. Tracers rose from the convoy in response. The Mitchell continued directly toward the bow of the nearest transport. At approximately 1,500 yards, the pilot aligned the aircraft along the vessel's longitudinal axis. "Stand by," he said. The loader inserted a round into the open breech and stepped clear. The first cannon shot was fired at roughly 1,200 yards. Observers in accompanying aircraft later reported a visible impact near the waterline forward of the bridge. The recoil caused a perceptible nose drop and slight deceleration, as recorded in post-flight notes. The pilot corrected immediately and closed distance further. A second round was loaded under increasing anti-aircraft fire. "Ready?" the loader called. At approximately 900 yards, the second shot was discharged. This round struck near midships. Smoke and debris were observed rising from the deck area. The Mitchell then banked away to port, descending briefly to under 200 feet before climbing to rejoin the formation. Skip-bombing aircraft followed, releasing bombs that ricocheted into the transport's hull. Combined fire from multiple passes left the lead vessel burning and slowing. The second transport was engaged primarily by bombing and strafing aircraft, while the destroyer maneuvered and generated dense defensive fire. After-action reports credited the 75mm cannon with 2 confirmed hits on the lead transport. Reconnaissance later that afternoon indicated the vessel had been abandoned and was either sinking or grounded near the shoreline. The destroyer and second transport withdrew under cover of smoke. Crew accounts emphasized both effectiveness and limitation. The pilot noted that accurate alignment required a straight approach of several seconds under concentrated fire. "You get 1 clean shot," he told an intelligence officer after landing. "Maybe 2 if everything holds." The loader reported physical strain while handling heavy rounds during evasive maneuvers. Enemy air defense proved intense, but not coordinated with fighter cover on that occasion. Several B-25s sustained minor damage from light automatic weapons. No aircraft were lost on the mission, though one returned with control cable impairment caused by shrapnel. The sortie demonstrated that the 75mm cannon could deliver precise, destructive fire against transport-class vessels. However, the limited rate of fire and vulnerability during the attack run were clear. Post-mission evaluations recommended tighter coordination with suppressive strafing and emphasized firing at closer range to improve hit probability. This first operational use in June 1943 established both the potential and the constraints of the cannon-armed Mitchell. Field experience began influencing adjustments in approach profiles, ammunition selection, and formation timing. The weapon had proven viable in combat, but continued operations would determine how tactics evolved in response to its strengths and limitations. By late 1943, Units operating the 75mm B-25G in the Southwest Pacific had accumulated enough combat experience to adjust their methods. Early missions demonstrated that the cannon could inflict concentrated damage, but only when integrated carefully with other attack elements. The 5th Air Force gradually refined a combined arms approach that emphasized coordination, volume of fire, and precise target selection. Integration with forward-firing .50 caliber machine guns became central to this adaptation. Additional gun packages were installed in the nose and fuselage, allowing cannon-equipped aircraft to deliver sustained strafing fire during approach. Crews learned that machine guns suppressed deck gunners more effectively than a single cannon round. One pilot summarized the lesson during a briefing. The 50s keep their heads down. The 75 does the heavy work. The combination allowed the aircraft to engage both personnel and structural targets in a single pass. Skip bombing remained a parallel technique. In coordinated attacks, one element would approach at mast height and release bombs designed to ricochet into the hull near the waterline, while cannon-armed B-25s executed direct fire runs, either immediately before or after. Timing was critical. Strafing aircraft initiated suppression. The cannon aircraft aimed at specific structural points, and bombers completed the strike with explosive payloads. Mission commanders emphasized strict sequencing to avoid collision at low altitude. Target prioritization evolved as well. Crews were instructed to aim armor-piercing rounds at engine compartments or directly at the waterline to maximize flooding potential. High-explosive shells were used against lighter vessels, barges, and exposed deck installations. Supply barges operating along the New Guinea coastline proved vulnerable to cannon fire. A single well-placed hit could disable propulsion or ignite cargo. Larger transports required multiple coordinated passes to achieve decisive results. Comparisons between cannon fire and concentrated machine gun fire revealed trade-offs. The 75mm delivered significant penetration and internal damage with a single hit. However, .50 caliber guns produced sustained impact over a wider area and allowed greater flexibility during maneuver. In practice, machine gun strafing accounted for a higher number of damaged smaller vessels, while the cannon was reserved for selected high-value targets. Crew coordination procedures were standardized. The pilot maintained a steady attack vector, minimizing lateral movement. The co-pilot monitored airspeed and engine settings. The loader prepared the next round immediately after recoil recovery. Intercom communication became concise and formulaic. Range calls, readiness confirmation, and breakaway commands. Training emphasized that hesitation during the final seconds of approach increased vulnerability. Survivability at low altitude remained a primary concern. Japanese defensive fire improved noticeably through late 1943. Ships added additional automatic weapons, and shore-based units positioned light anti-aircraft guns along likely approach corridors. Crews reported denser tracer patterns and more accurate fire control. Damage reports showed an increase in hits to control surfaces and engines, though armor protection and rapid breakaway maneuvers limited losses. Statistical evaluations of after-action reports indicated mixed results. In several operations, cannon hits were directly linked to sinking or beaching transports. In others, damage assessments attributed primary destruction to skip bombs or cumulative strafing. Analysts concluded that while the 75mm was effective against certain classes of vessels, it was not universally decisive. There were situations in which the cannon proved critical. Attacks against reinforced merchant hulls or vessels carrying fuel often required penetration beyond the capability of machine guns. Conversely, against small maneuvering barges or dispersed coastal targets, the slower rate of fire limited effectiveness compared to concentrated machine gun bursts. By early 1944, discussion within operational units reflected an ongoing debate. Some officers argued that heavy airborne cannons represented the future of maritime interdiction. Others questioned whether weight, recoil, and limited ammunition justified the modification when massed machine gun fire and improved bombing techniques were yielding consistent results. The experience of the 75mm B-25 had reshaped tactics, but it also raised a broader question: whether large-caliber guns would define the next stage of air attack. Doctrine. By late 1943 and into 1944, the operational limitations of the 75mm B-25 concept had become increasingly apparent within the United States Army Air Forces. While the cannon-armed Mitchell had demonstrated that a medium bomber could deliver direct, heavy-caliber fire, sustained combat operations exposed constraints that affected its long-term viability. One of the most significant limitations was the low rate of fire. The M4 cannon required manual loading after each discharge. Even under ideal conditions, the practical rate rarely exceeded 3 or 4 rounds per minute. In contrast, by 1944, aircraft rockets, such as the 5-inch high-velocity aircraft rocket, could be fired in rapid succession. A single fighter bomber could release multiple rockets within seconds, saturating a target area. During a tactical conference, one operations officer remarked, "With rockets, we can put 8 warheads on a ship before a gun crew can load its 3rd shell." The comparison was not exaggerated. The increasing effectiveness of air rockets in 1944 further reduced the relative advantage of the 75mm cannon. Rockets required less structural modification to the aircraft and imposed no internal recoil loads. They allowed attacking aircraft to break away immediately after launch, reducing exposure time. As production increased and accuracy improved through better sights and training, rockets offered a more flexible solution for anti-shipping and ground attack missions. Maintenance burdens in tropical environments also affected the cannon-equipped B-25. Operating from forward airstrips in New Guinea and the Philippines, crews faced constant humidity, corrosion, and abrasive dust. The cannon's recoil system and breech mechanism required regular cleaning and lubrication. Armorers reported accelerated wear in recoil cylinders and mounting brackets. It's artillery maintenance inside an airplane, one crew chief noted. Every shot means another inspection. They added workload, strained limited ground personnel resources. Ammunition storage posed another constraint. The B-25G and H variants could carry approximately 20 rounds for the 75mm weapon. This limited engagement time during combat. Once expended, the aircraft relied primarily on machine guns. Compared to hundreds of .50 caliber rounds carried aboard later variants, the cannon's ammunition supply was modest. Storage racks also occupied space that might otherwise be used for fuel or additional ordnance. Structural load after repeated firing cycles became a long-term consideration. Although the reinforced nose section distributed recoil forces effectively, cumulative stress affected rivets, skin panels, and internal frames. Maintenance logs documented recurring inspections of forward fuselage components. While no widespread structural failures were recorded, the requirement for continual monitoring increased downtime. International comparisons highlighted similar challenges. Other air forces experimented with large-caliber airborne guns, including British and German heavy aircraft concepts. These projects likewise encountered trade-offs involving weight, recoil, and limited ammunition capacity. The technical feasibility did not always translate into operational efficiency. As a result, later B-25 variants emphasized concentrated forward-firing machine guns rather than heavy cannons. The B-25J, for example, could mount up to 14.50 caliber guns in various configurations. This provided sustained suppressive fire, higher effective rate, and greater flexibility against dispersed targets. The shift reflected practical experience gained in the field. A cost-benefit analysis conducted within operational commands weighed combat effectiveness against logistical and structural demands. The 75mm gun delivered powerful single impacts against selected targets, particularly medium transports and fortified positions. However, rockets and massed machine gun fire increasingly achieved comparable or superior results with less complexity and lower maintenance cost. At the doctrinal level, USAAF leadership reassessed the role of heavy guns in medium bombers. Emphasis shifted toward adaptable, multi-role platforms capable of delivering high volumes of fire without extensive modification. The cannon-armed Mitchell influenced tactical thinking, but it did not define future procurement priorities. In retrospect, the 75mm B-25 represented an experimental but influential adaptation. It demonstrated American willingness to modify existing aircraft to meet urgent operational needs. Its limitations were instructive, shaping subsequent developments in air-to-surface weaponry and contributing to the broader evolution of attack aviation doctrine during the Second World War. By the end of World War II, the B-25 Mitchell, armed with a 75mm cannon, had secured a distinct, if limited, place in American aviation history. The Gand-H variants represented a deliberate attempt to combine medium bomber range with heavy direct fire capability. In total, approximately 405 B-25G aircraft and 1,000 B-25H aircraft were produced. Though never the dominant version of the Mitchell, they marked a significant technical departure from conventional bomber design. In combat, these aircraft operated primarily in the Pacific theater, particularly in New Guinea, the Bismarck Archipelago, and later in the Philippines. Assigned mainly to units of the 5th Air Force, they were used against Japanese transport ships, coastal installations, and supply barges. The 75mm cannon proved capable of penetrating hull plating and damaging engine compartments when accurately employed. Combat reports credited cannon hits with disabling or contributing to the sinking of multiple vessels, particularly lightly armored transports operating close to shore. The concept influenced later thinking about concentrated forward firepower in aircraft. While the large cannon itself did not become standard in American medium bombers, the emphasis on forward-firing weapons did. Subsequent B-25 variants replaced the heavy gun with multiple .50 caliber machine guns, reflecting a preference for sustained fire over single heavy impacts. The idea of specialized ground attack aircraft continued to evolve, leading in later decades to dedicated platforms such as heavily armed attack aircraft designed specifically for close air support and anti-armor missions. Compared to those later specialized combat aircraft, the 75mm B-25 was an intermediate solution. It adapted an existing bomber rather than designing a new airframe around a specific mission. Later aircraft concepts would incorporate lessons about structural reinforcement, recoil management, and pilot workload more systematically. The B-25G&H demonstrated what was possible, but also revealed practical constraints related to weight, maintenance, and rate of fire. Several surviving examples of cannon-armed B-25s are preserved in museums in the United States. Restored aircraft can be viewed at institutions such as the National Museum of the United States Air Force and other aviation collections, where the distinctive solid nose and protruding barrel remain immediately recognizable. These preserved airframes serve as technical artifacts, illustrating both ingenuity and urgency in wartime modification. Contemporary historians generally assess the 75mm Mitchell as an innovative but situational adaptation. It addressed a specific operational challenge in the Pacific, where Japanese shipping required aggressive interdiction at low altitude. At the same time, scholars note that rockets and massed machine gun fire soon offered comparable effectiveness with greater flexibility. The heavy cannon added maintenance complexity and imposed structural stresses that limited its broader adoption. The concept did not become standard doctrine, largely because it solved a narrow problem within a rapidly changing technological environment. As air-to-surface rockets improved in 1944, they delivered high explosive power without the recoil and weight penalties of an internal cannon. Command-level reassessments favored adaptable armament packages over singular heavy weapons. Symbolically, however, the cannon-armed B-25 holds a distinct place in the air war over the Pacific. It represents the determination of American air forces to innovate under pressure, modifying available aircraft to meet immediate operational demands. The image of a medium bomber carrying what was effectively a tank gun in its nose remains a reminder of the improvisation that characterized much of the conflict. A balanced assessment must recognize both innovation and practicality. The 75mm B-25 was neither a failed experiment nor a universal solution. It achieved measurable combat results, influenced tactical development, and contributed to the broader evolution of ground attack aviation. At the same time, it demonstrated the limits of adapting heavy artillery to aircraft without compromising flexibility. In times of war, adaptation often precedes perfection. The cannon-armed Mitchell stands as evidence that urgent necessity can produce bold engineering choices, even if those choices are later refined or replaced. If you found this examination valuable, consider leaving a thoughtful comment about which World War II aircraft innovation you believe had the greatest long-term impact. Your engagement helps sustain serious historical discussion.